29. Determine the standard cell potential and the cell potential under the stated conditions for the electrochemical reactions described here, and then state whether each is spontaneous or non-spontaneous under each set of conditions at 298.15 Kelvin. And then we have letter C. So in this case, we have a cell made of a half cell in which 1.0 molarity aqueous bromide is oxidized to 0.11 molarity bromide ion, and a half cell in which a aluminum ion at 0.023 molarity is reduced to aluminum metal. Okay. So in this case, a lot of words here to just determine two things. We need to find out the standard cell potential and just a regular non-standard cell potential. Remember that a cell potential is always a E cell. So that's what we're looking for here. Standard just means that you're searching for a E standard cell. There should be a notch on the top here. As opposed to just finding an cell potential, you're solving for a E cell that has no notch there. Okay. Now they did tell us that we had a temperature value. So that is at standard conditions. So 298.15, that's a standard temperature. And it seems like we're also using that temperature to find out the cell potential that's not standard. Now, before we get started, let's just divvy this up because I want to have one side for standard and the other side for not standard, basically. Not standard. Okay. So in this case, we're trying to find out that E subcell, or not sub, but, the E notch cell. And this one, we're just trying to solve for E cell. So, since we're solving for a standard cell potential, we are allowed to go in the back of a textbook to find out what the half reactions are for what they stated here, with their corresponding cell potential values. Now, the reason why I pulled these two half reactions is because the context they gave me, we have aqueous bromide, so I got bromine, is going into a bromine ion, right? So it seems like I'm talking about bromine here. Bromide means that you're using the diatomic, so you have to have one Br2, and then a bromide ion would be the negative. An ion just means that you have a charged element, and that's the first equation. That's why I pulled that equation from the back of the textbook. The second one was talking about an aluminum ion, so that's Al. Aluminum loves to be a 3+ charge, and it's just reduced to aluminum metal. So I went in the back and I found, there's the Al3+ and the aluminum. So I pulled that number. Now, what formula are we going to use these values? Well, good question. The formula is this. Notice how there's all notches at the top, right? Those little degree signs, that's all standard values. So basically, in order to find out the standard cell potential, I just need to find out the standard cathode number minus the anode. Here's the two values, but which one is the cathode and which one is the anode? Well, remember, red cat and anox. Red cat means that the cathode is always reduction, or something is being reduced. There's that red cat, red and then cat. And then vice versa, we have oxidation happening at the anode. So that's anox. So maybe that helps us. When they were talking about the bromine, they said that it was oxidized. And oxidation always happens at the anode, so we know that the bromine half reaction is the anode one. Vice versa, when they talked about the aluminum, they said that the aluminum one was reduced, and reduction is always the cathode. So we know that the aluminum half reaction is going to be the cathode, and the bromine one, right? Doesn't matter if you put maybe I'll just put Br2. The bromine one is the anode. Now, it doesn't matter what the balance equation is, you're never going to be multiplying these numbers by 2, by 3, no coefficients in your balanced equation. So for right now, we don't even need a balanced equation. So my E cell would just be the cathode value, which was the aluminum one. So it's going to be the negative 1.662. And I'm going to minus with the anode value, that was this one, 1.0873. And I just want to point out here that if you're doing cathode minus anode, which I highly recommend, you do not have to change any of your E values. The negative here does it for you. It just makes it easier. Okay, so now we have an E cell of negative 1.662 minus 1.0873. I'm just making sure that I plugged everything in correctly. Looks good to me. We could only go out to the thousandths place, so this would be a negative 2.749 if we were considering sig figs, and that is in volts. So that's your standard cell potential. Now, is this spontaneous or non-spontaneous? Well, that just goes by knowing your signs. If you have a positive E cell value, that's always going to be a spontaneous reaction. If it's a negative, that means it's non-spontaneous. So here, since we clearly have a negative value, this negative means that it's non-spontaneous. Okay. So half of the question done. But, spoiler alert, I am going to need much more room. You're probably, I hear the crying already, but we got to do it. I'm going to need much more room for the non-standard, so I'm pulling this up, giving myself as much room as I can. Okay. So now here comes the big one. We now want to find out the general cell potential, not standard, the general E cell. So I say to myself, okay, what information do I have? I have a standard cell potential now. I have a temperature. They gave me these molarities. Is there anything, any formula that's come into your mind that groups all these together? Just an E cell, an E standard cell, a temperature value, and molarities. Yeah, there is one. There's one, and there's only one. And that formula is this. It's a much bigger formula. That's why we need a little bit more room. So maybe I'll pull this down a little bit. Maybe I'll even... Whoop, I can't do that. There we go. I'll pull that up. We'll pull this up a little bit just to give myself as much room as I can. All right, so the non-standard E cell is the standard cell potential minus R times T divided by N divided by F, and then times ln of Q. Oh boy. Let's start with this mumble jumble mess over here. Now, since we're dealing with volts, right? E cells are in voltage. That's inside of voltage are joules, a form of energy. So your R value for this formula can only be the energy one, which is 8.314. Temperature, we got to have it in Kelvin, but thank goodness they gave it to us in Kelvin. So 298.15 Kelvin. I'm going to skip over the N for now. Let's go to F. That's Faraday's constant, another constant number, 96,485. If you wanted to know the units there, it's just coulombs per mole. But, no biggie. You don't need to know the units. Just know that it's 96,485. And now, before we do the N value, I just want to say that, hey, we did find that standard cell potential. It's the negative 2.749 volts. Okay, now let's discuss this N value. Now, the N value is generally a form of moles. But since we're talking about oxidation and reduction, we have to be a little bit more specific. The N value here is specifically the moles of electrons. So the E minus, that's transferred. So this comes from your half reaction, right? Now, when you look at your half reactions, you say a little nice saying in which you hope that they gave you half reactions that have the same number of electrons. If they give you the same number of electrons, the half reactions basically are already balanced and you don't have to do anything. But unfortunately here, I have 2 electrons and 3. In order for this to work, I have to have the electrons being the same in order to be transferred, right? One can't transfer 2 and the other accept 3. That wouldn't make sense. There's no electrons that are not accounted for, so the transferring has to be the same number. So you say to yourself, well, what can I multiply by these equations to get the same number of electrons? The next lowest number up that 3 and 2 have in common is 6, right? Technically, I can times the first one by 3 and the second equation by 2. And then each electron would be 6. And that's the number of electrons that were transferred. So just be careful on that. Our n here is 6. So just to recap, we have the standard cell potential. R is a constant. They gave you the temperature. We just found out that there's 6 electrons being transferred, and F is a constant. The only thing left is this Q value. Now remember, Q goes with a K value, an equilibrium constant. In order to find out the Q value, I have to do products divided by reactants. Remember that formula? Right? Products raised to the coefficients divided by reactants raised to the coefficients. But where's the products and where's the reactants? I don't have a balanced equation. So now we actually have to take these two half reactions and make an equation, which I'm going to be doing over here. But the good thing is that we already found out what we're multiplying them by. But now the next thing is we just have to make sure that we state which one was the cathode and which one was the anode. We did say that the aluminum was the cathode. So this is the cathode. And anytime that you have electrons on the left side of your equation, that's always going to be representing the cathode, reduction. So since the electrons are on the correct side, I'm literally just going to write down this equation again. But I'm going to distribute the 2. So instead of just one Al3+, I will now have 2 Al3+. And that's a charge, so that's aqueous. Plus 2 times 3 is now the 6 electrons. Yield, I have now 2 aluminum solids. And that's good to go. But now, the trouble a little bit is the anode. The anode should always have electrons on the right side of the equation. But all of the half reactions that you see in the back of a textbook is always going to give you cathode values. So if I want to turn this into a cathode, what am I going to have to do with this equation? Yeah, I heard you. You just got to flip it. So what I'm going to do is I'm going to flip this equation and times it by 3. So I'm not going to have 2 Br minuses anymore. 2 times 3 is now 6. I have 6 Br minuses. And that's a charge, so that's aqueous. Yields, I now have 3 Br2 aqueous plus the 6 electrons. And now, since my electrons are balanced, they're 6 and 6, and if you notice, they're on opposite sides. That means that they can cancel. And maybe I'll just put over here that this was the cathode and this was the anode. And now, what we're going to do is we're just going to add them together. Cancel out the like electrons. Bye-bye. Bye-bye. And just rewrite what else you got. So we got 2 Al3 plus aqueous plus 6 Br minus aqueous yields, we got 2 aluminum solids plus 3 Br2 aqueous. Here's my balanced equation to now get the Q expression. Because Q is concentration of products over reactants raised to those coefficients, right? So, keep in mind that no solids or liquids allowed. This aluminum is a solid, so I don't care about it in my expression. This is aqueous, so I'm going to include that. So this has to be the concentration of Br2, and I have to raise it to the coefficient. There was a 3 here, so I have to raise that to the third. Now I come over to my my reactant side, they're both aqueous, so they're both going to get included. The aluminum should be raised to the second, and the bromine should be raised to the sixth. So let's just do that. We have the aluminum being raised to the second, the bromine being raised to the sixth because of those coefficients, and now I have Al3+, and that makes sense, and then the Br-. Okay, the next step is, what is the numbers that go here? Yeah, I told you, there was a spoiler alert. But anyway, now let's go back into the question to find out what these values are. Now keep in mind that the bromide was the Br2, and they told us that that was 1 molarity. So I had 1.0 molarity for the Br2, so this is going to be 1.0. The aluminum, Al3+, let's see, they said that the aluminum ion was 0.023 molarity, so that's this. And the bromine ion, which was that guy, is 0.11. And I just want to make sure that, yep, that's a 0.0. Okay, so now we're going to plug in. Q equals, we have this raised to the third, this raised to the second, this raised to the sixth. Let's just plug those numbers in. 1.0. We got 0.023 and then 0.11. Now, 1 raised to the third is always going to be just 1, right? So I could just leave this as 1 if you want. Maybe I'll just put 1. And now I can plug this all into the calculator at once. If you want to do it in 2 steps, you can. You can find out what this is and then do the division. But I'm going to try to just cram this all into 1 step because the TI-84 lets me do that. So I'm going to say 1 divided by. Now all this is going in at the same time. So, and you know, I mean, it doesn't really matter. I guess I'll just show you guys, right? Parentheses, 0.023. I'm going to raise that to the second. And then I'm just going to keep going on. I'm going to say 0.11 raised to the sixth. Close the parentheses. So by doing this, you see how the division is all in those parentheses. So I'm going to press enter. And I get a big, big, big number. 106705. And more numbers. So that's the Q. Keep in mind that this is not the final answer, so you really shouldn't be rounding. That's another reason why I love the TI-84, because I can just keep pulling stuff down here, right? So let's see. And just to show you guys, if we did it in 2 steps, let's just see if we get the same answer. So I'm going to say 0.023 raised to the second times by 0.11 raised to the sixth, right? And then I'll just do 1 divided by that answer. You will see that the same answers are there. So we are good to go. And maybe just for now, whoop, what happened here? Clear that out. Maybe I guess I'll just put the last 4, 8, 4, 6, 9, right? So this would be, oopsie poopsie, 8, 4, 6, 9. Okay. Pause the video if you need to. I just have to erase the Q value because we just need more room to just actually do the final calculation. So I'm just going to get rid of all this. And now let's get going. Maybe I'll just put this N value over here. And now we are ready. The final steps are upon us. E cell equals the E standard cell, which was a negative 2.749, minus, I have that ratio, I have the ln of that big number, and I have the 4 values up here, so 1, 2, 3, and 4. Let's just plug those in quick. The R value is the 8.314. The temperature was the 298.15. 6 electrons that were transferred, and 96,485. And then finally, the ln of this huge value, which was the 11067058469. Okay. Big suggestion here, get rid of this, right? Just make this into one nice number. So that's the first thing that I'm going to do. I'm just going to simplify that. So E cell equals negative 2.749 minus, let's see what this number is. So I'm going to say 8.314 times 298.15 divided by 6. And since I'm not using parentheses here, I'm just going to press divide again to get that Faraday's constant in the denominator. I'm just checking. Everything looks good here. Press enter. And now I have 0.00428, etc., right? Don't round because that's not the final answer. And this was that whole big number, 1067. Every time I say 1067, my mind just auto-completes and it says, Light FM, 106.7, Light FM. Anyway, 10670588469. That's like a little insight into my brain. 8469. Now what I would do is I would multiply these values together, or you could even just plug this all in into one shot. Doesn't matter. E cell equals negative 2.749. And I'm going to say this value times by the ln, and then I'm going to just grab that value, right? Doesn't matter which one I use, they're the same. Close the parentheses if you want to. Okay. So this is a minus 0.0890 with much more decimals after that. Finally, negative 2.749 minus that answer. And there we go. And I guess I'll just put it over here. E cell equals negative 2. And how many decimals do I need? I guess 838. And that's volts. Once again, we just have to say if this is spontaneous or non-spontaneous, but I also see that it's negative, so this is non-spontaneous as well. And oh my goodness, this one is done. What'd you think? If you can do these problems, this section on the exam or quiz is going to be great. These are very, very, very challenging, especially because you have to make your own equation. You have to know how many electrons are being transferred. You have to know how to use the cathode and anode values correctly. So if you can get this down, a lot of concepts are here. So you should be good to go. I hope you're all having a great day. Let's keep studying hard. And thank you so much for supporting the channel and helping us grow by just, watching the video and learning from the video. And telling your friends, telling your classmates. Some of you I know have spread the word in your classes. Thank you so much for that. My brother and I, we truly do appreciate all of you. And let's just keep learning. All right? I will see you soon. Bye-bye.